All right, so end of class yesterday, we had kind of just finished up our first vector addition example where we had vectors that were perpendicular, right? We had that car and it had gone 275 meters east, and then it had turned and gone 125 meters north. Okay, and we were asked to calculate its total displacement. Right, so when we did that, what we said was, okay, the total displacement of that object is its change in position. Its initial position was here, its final position was here, so the displacement would be represented by this line. Okay, is that ringing a bell from yesterday? All right, how did I calculate the length of that line? I use Pythagorean theorem, right? I have the two sides. I have, this is 275, this is 125. Okay, so I said, all right, if that line represents the displacement, then the magnitude of the displacement was a squared plus b squared. Okay, and then when we did that, I think it came out to 302 meters. All right, were we done at that point? What else did we have to find?
Direction.
We had to find the direction, right? Because displacement is a vector quantity. This only tells me its magnitude. I still need direction. Well, the direction is this angle right here. Okay, that's going to tell me which way it's going if I can calculate that angle. Now, since I know all three sides of that triangle, can I figure out that angle? Could I have figured it out even if I only knew two of them? I could. Okay, so what I like to do, I mean at this point, because we know this side's 302 and we know you could use sine, cos, or tan, okay, to get that angle if you wanted to, right? For me, I have a favorite trig function because I'm that much of a geek, okay, but it's tan, okay? And the reason that I want to use that here is because I didn't calculate this number and I didn't calculate this number. So if I messed up this calculation, I'll still get the angle right because these weren't the numbers I calculated. Okay, that's just me, right? But you could use any trig function you wanted. So if I'm looking for this angle here, and I'm using this side, which is opposite that angle, and this side, which is adjacent to that angle, I'm going to do this. That the tan of theta equals 125, the opposite side, divided by 275, the adjacent side. Everybody okay with that? All right. So to find theta then, I just go inverse tan of that. Okay, and then I get that angle. So I think it came out to 24.4, if I remember correctly. Okay, so inverse tan, okay, of 125 divided by 275. Oh man, mind like a steel trap. Okay, all right, so 24.4 degrees. Okay, would be my angle there, so I'm just going to write that in, 24.4 degrees. But what do I need to put on that? Right, I need to, like, that angle is fine, but the question told me east and north, so I need to say it's 24.4 degrees measured from here going this way. I can't just leave it as 24.4, okay? There could be lots of 24.4 degree angles, okay? I don't know which way that 24.4 degrees is going. So what I need to say is, here's the angle that I drew. I'm measuring it from this direction, which is east, and going which way from there? North. So this is north of east. Okay, I just get that from knowing how my compass works, okay, or actually having drawn it out, which lots of people do. Okay, all right, so I'm starting on east and I'm going north of east. There's my 24 degree angle. Okay, it's north of east. Okay, Everybody all right with that? Okay. Ringing a bell? Okay. Here's what I want you guys to do. Okay. When I drew these vectors, I drew them which way? Tail to head, right? I drew the 275 and then I drew the 125 like I was telling a story. First this one happened, then this one happened. It's important we draw our diagrams that way. So what I want you guys to do is to draw the diagram for this question and then see if you can calculate this person's displacement over the whole trip. Okay, I'm going to give you guys a few minutes to work on it. Okay, good. I'm just going to draw the diagram just in case anybody's kind of stuck on getting started on this one. Okay, so the camper left her tent to go to the lake. She walked 0.8 kilometers south, then 1.2 kilometers east, and then 0.3 kilometers north. Okay, so what she did kind of is going to look like this. And that's going to be my 0.8 kilometers. Then she went 1.2 kilometers east. Okay, so I drew it tail to head, right? First she did the 800 meters, then she went 1.2 kilometers east. Okay, and then she goes 0.3 kilometers north. Okay, I think my scale's okay there, right? That 0.3 could maybe be a little longer or the 0.8 a little shorter, but it generally gets the point across. Okay, so that's what she did. They want her total displacement. Where would I draw a line that represents her total displacement? Okay, here's what we have to remember, guys. Displacement is your change in position. Where was her initial position? Up here, top of the blue line, right? So this was her initial position. Where's her final position? Top of the purple line. Okay, so at the top of the purple arrow is the final position. So is my displacement supposed to be a line directly between my initial and final positions? Okay, so I just get to play connect the dots, right? Okay, I mean, that's what it comes down to at the end. Okay, this line here is her change in position or displacement. Right. Now, the last question we did, I managed to make a right triangle out of that displacement. Can I still do that? Okay, see if you can get it from there. Okay, there are two correct answers for this. Your magnitude will be the same regardless of which answer you had, but it's possible that you could get a slightly different angle, okay? But they'll be complementary, right? Like if one of you got 30, the other one would have got 60. Okay, they'll be complementary. It just depends which way you drew the triangle. So here's what we have to understand about this trip. In the end, she has gone somewhat east and somewhat south, right? She's ended up southeast of where she started, right? And I need to make a right triangle in order to calculate that overall displacement. All vectors can have a right triangle, okay? And they have to in order for us to do what we want to do with them, okay? So for this case, one of the, what we call components of that displacement vector is horizontal, or the x component, if you're talking about an xy scatter plot. Okay, so an xy plot, okay, this would be our horizontal or x component, and it goes east. How long is it? 1.2 kilometers. It's 1.2 kilometers. Okay, she also went south. That's the vertical component of that vector, or the y component. How long is that? 0.5 kilometers, right? Because she went 0.8 kilometers south and then she came back 0.3 kilometers. So she only ended up half a kilometer south vertically of where she started. Okay. All right, so could I have also drawn the triangle this way? And if you did, totally fine. Your answer will be right, you'll just get the other angle. Okay. So, can I now figure out the magnitude of her displacement? Same way I did with the other one, right? I'll use Pythagorean theorem. Okay, so D will be the square root of 0.5 squared plus 1.2 squared. Okay, so that's going to be 1.3 kilometers. Okay, and I also need to know what direction. Southeast is not specific enough. I need to know what angle, for me, south of east, this person went. If you drew it the other way, it'll be east of south. Okay? So for me, I'm going to calculate that angle using tan, my opposite side and my adjacent side. Okay, so I'm going to say that theta will be the inverse tan of 0.5 divided by 1.2. Okay, so I get 23 degrees there. Okay, so if you got 57 degrees east of south, you're good. Okay, you just got the complementary angle. Okay, sorry. Yeah. 60, 50, 67. 67, not 50, 67.
If you did like drew it the other way, but you got 22.6 but north of west, like.
So then you calculated the one down here, right?
Yeah.
Okay, is that the way she went?
Guess not.
Right, so you always want to pick an angle that's pointing from beginning to end. Does that make sense? What I tell people is if you're not sure, when you draw this angle arc, draw a circle around your starting point and you'll know which angle to get. Wherever that goes through your triangle, that's the angle you want to find because it's the one that'll point from beginning to end. Right? Otherwise, you're telling them how to get back. Right? All your math is right, but the reference point is backwards. Okay, everybody okay with that? Right? So here's what we need to get out of an example like this and the one we did before. Okay? Vectors come down to how far horizontally and how far vertically did you go. You can break any vector down into a right triangle where you can use trigonometry. Okay? So no matter how many parts there are to the trick, wherever they end up, they're going to be X amount over and Y amount down, or Y amount up, or whatever, whichever way they went. Okay? But in the end, you'll always be able to have a final triangle that has a horizontal and a vertical component with which you can use then to find the information you need. Okay? All right, any questions on that? Okay. We already did that one. Where's the one I was looking for? Okay, let's do this. I'm just going to write one out and I'll have you guys try it. Okay. I gotta get back into that swing of handwriting. I apologize for my handwriting. It's been a while since I wrote on the board. Okay, so band is marching on a football field. The band marches due south 20 meters, then reverses and marches 5 meters north. The band finishes by turning west and marching 8.5 meters. Okay, what is the total displacement of the band? All right, give you a few minutes on that one. Okay, draw your diagram out, do your tail to head stuff, okay, so that you get that triangle that you can use. So we got this band marching on the football field. The first thing they do is go due south 20 meters. So they do this. And then it says they reverse and go due north 5 meters. So tail to head, 5 meters. And then they go due west 8.5 meters. Okay, my scale's okay. It's not perfect, but it's going to get the point across. Right? Where would I draw an arrow or a line that represents the band's total displacement?
From the top of the 20 meter to the end of the 8.5.
Right. Okay, this is their final position. This is their initial position. So I could draw a triangle this way or back over top of my other lines. I don't like to do that because it looks kind of busy. Okay. So there's going to be my total displacement, right? I know that the band ended up going somewhat west and somewhat south over the course of this trip. Okay. How far south did they go? 15 meters, right? They went south 20 and then they came back 5 north. So, okay, if I'm taking my two y components, I know it's 20 minus 5 for 15 meters south. Okay, I also know that they went how far west? 8.5 meters. All right, well now I've got my triangle. Okay, I know they went 8.5 meters west, they went 15 meters south. Now I can figure out their total displacement using Pythagorean theorem. Okay, so 8.5 squared plus 15 squared. Okay, so 17.24 meters, that's the magnitude. And now I've got to find the angle. So the way I drew it, the angle is here. It'll be south of west. If you drew it this way, it'll be west of south. All right, so for me, that's going to be theta is tan to the minus 1 of 15 divided by the adjacent side, 8.5. Okay, so for me it's 60.5 degrees, and that'll be south of west. So if you got 29.5 degrees west of south, you're also good. Okay, everybody all right with that? So every trip has got to break down into how far did you go horizontally, okay, here along the x-axis, and how far did you go vertically along the y-axis, up or down. All right, significant digits, okay, because that's, maybe some of you have done that, maybe some of you haven't, okay. So the question always comes up, what do I round to, okay, things like that. So what we use in high school science is the rule of significant digits, okay. Significant digits is something we use so that any math that we do doesn't suddenly increase or decrease the accuracy of the measurements we used to do that math. All right, so for example, if I divided, or if I, let's say, added these two numbers here, okay, let's say I was adding 8.5 to 9.2178, okay, is one of those numbers measured more accurately than the other? Okay, but when I add them together, I can't have the sum be more accurate than the least accurate part of it, can I? Right? There's, after this number for the 8.5, I didn't measure anything. That means even though these numbers are gonna carry over when I add together, right? So we'll have 8, 7, 1, 7, and 17, okay? I can't keep those numbers. They're uncertain now because I added them to a number that wasn't measured as accurately as the others. Okay, everybody okay with that idea? So significant digits, just make sure that whatever math we do doesn't suddenly make our measurements better. Because it doesn't. I can't do math and change how I measured something. Okay? So our general rules are as follows. With addition and subtraction, you do it just like I did here. Okay? Whatever the least accurate number is, that's the decimal place you keep. Okay? And you don't go past that. For multiplying and dividing, you go with the least number of significant digits. Now, you're probably going, okay, what's a significant digit? Any measured value is a significant digit. So if I have, let's say, 8.7 and I'm multiplying it by 5.89, okay, that number has how many significant digits?
2.
This one here, 5.89, has 3. This one has 2. Okay? Any number that's not a 0 is significant. Sometimes 0 is significant if it's a trailing 0. Leading zeros are not. So difference here, 8.70. Would I bother to write that 0 if I didn't measure it? Right? If I wasn't certain of that 0, I wouldn't have written it there. That means I measured it. That number is significant. How many significant digits in that number? 2. Okay? Why? These are leading zeros. There wasn't anything to measure here. Right? The first number I measured was smaller than all of these. There was nothing to measure in these, therefore they're not significant. But that 0 is. I wouldn't have written it if I wasn't sure it was actually a 0. Okay? So leading zeros, never significant. Trailing zeros, always significant. Every other number not 0, always significant, because you wouldn't write it if you didn't measure it. Okay? For physics, most of the time what this comes down to is if I had a problem like the one we just did, okay? So, well, all my numbers had how many significant digits? 2, right? That had 2, that had 2, that had 2. How many significant digits did my answer have? 2. Okay? As soon as you do more than one calculation, that's what it comes down to. Okay? I just look at my givens, and if I use that number, then it counts. Okay? So my final answer here should round out to 17 meters at 61. Actually, this was 60.4. I rounded that up, didn't I? I did. Okay, so it's not going to be 61. Because this was actually 60.47 or 46 or whatever it was. So, okay, if I'm looking at this, the 4 doesn't round the 0 up. 60 degrees south of west. 2 significant digits in my answer. Okay? 99.9% of the time, that's what significant digits are going to come down to. I look at my givens, and it's the smallest number of them that I used. That's the number my answer can have.
Are you expected to write in scientific notation?
You will have to, actually, because if it ends up being like 100 or 155 and you only have 2 significant digits, you're going to have to go 1.6 times 10 to the 2. So yeah, you will have to use scientific notation a lot in this course. Yeah. Okay, so that's really all we have to know about the significant digit part. Okay, let's look at have you guys write this one down. We're going to draw the diagram for it. We probably won't get further along than that for this one. when you've got that one written down, draw the vector, draw the diagram, okay? Draw the tail of the head on there. And then we'll see, we'll draw it together after that, see how we do. Okay, so let's just look at the diagram here. If you're already past the diagram and you're flying on towards a solution, great, okay? But let's just kind of have a look at what the diagram will look like here. Okay, so the helicopter first goes 10.6 kilometers, 30 degrees north of west. So what I do when I get an angle like that is I draw a dotted line in the direction that it's measured from. It says it's north of west. So I drew a little line here that's west. And I'm going to go about 30 degrees north of that and draw my actual vector. Okay, that's going to be 10.6 kilometers in length, 30 degrees north of west. Okay, now if I follow that vector, I go both west, or horizontally, and north, or vertically. Would you agree? Okay. Then the plane turns and flies 18 kilometers south. Now here's where scale is important. Okay. Should this next line I draw be longer than the 10.6? Does that mean they end up way south of where they started? Okay, that's something I have to kind of visualize in my head before I start drawing lines, or I'm going to mess up my diagram. All right, so I'm just going to go, all right, 18 kilometers. Probably something like that, okay, reasonably to scale anyway. All right, so that means then that their initial position was here, and their final position was here. Agreed? All right, so where do I draw the line for their displacement?
From the red dot to the bottom of the pattern.
Right, from my initial position to my final position. Okay, that's what they ended up doing. They went south and they went west. Okay. Now, in all the other questions we've done, we had to figure out how far did they go horizontally, how far did they go vertically, so that we could get the sides of this triangle, because this line is our total displacement. And then this angle would be the direction for that displacement. Right? So here's what we're headed towards. I still want to do those same things, but now I might have to do just a little bit more trig to get there. All right? Overall, the helicopter went this far vertically. In this case, vertical is south. Okay? And it went this far horizontally. In this case, horizontal is west. Okay? In this purple triangle here, can I figure out how far west it went during that first part and how far north it went during that first part?
You use a sine or cos to figure out the opposite or the adjacent.
Exactly. I have the hypotenuse and I have an angle. If I have two parts of a triangle, I can figure out all the other parts of the triangle using trigonometry. Okay, so I would say your next step is to solve for this side, your x or horizontal or west component of this number, and your vertical or northerly part of that. Okay, see if you can figure out those two sides using trig. All right, give you a couple minutes on that, and then we'll walk through the rest of it. I think we'll have time. Okay, if I want to find purple x, okay, is that adjacent to the 30-degree angle? Okay, so which trig function am I going to use if I have the hypotenuse and the angle and the adjacent side? Cos. All right, so if I want to find x, well, purple x, not green x. And if I want to find purple x, okay, I'm going to go cos of 30 degrees times the hypotenuse, right? Because the cos of theta equals the adjacent side, which is the side I don't know, x, divided by the hypotenuse. So all I've done is manipulate and bring the hypotenuse over. Everybody okay with my math there? All right, so that's going to be cos of 30 times 10.6. So that's going to tell me how far west the helicopter goes. Okay, so I'm just going to write 9.18, but I'm going to keep all those numbers in the calculator. 9.18 kilometers west. Can I also calculate purple Y? Okay, and it's going to represent how far north the helicopter went during that part of the trip. Okay, now it's the I already did X. It's the opposite side. So what trig function am I going to use to solve for that one? Sine, right? I've got the hypotenuse, I've got the angle, I'm looking for the opposite side. So I'm going to go sine of 30 times 10.6. I think that should be 5.3 kilometers north, right? Okay. So now I know that this side is 5.3. Now that I know those sides, can I figure out what red Y and red X equal? Right, like red X should be what number? 9.18. I only went west here. That's the only time the helicopter went west ever during the trip. So the final displacement to the west is 9.18 kilometers because it's the only west part we did. Okay? So I can say that this side here is 9.18 kilometers. How far south did they go?
12.7
Okay, how'd you get that?
minus 5.3.
Right. I went 18 kilometers south, I subtract the bit I went north, the 5.3, and I get that this was 12.7 kilometers north. Can I solve for the rest of that triangle now? Okay, that's what we're moving to next week, called vector component addition. You guys will be just fine with it. Have a good weekend, but not too good.